So, welcome. Ooh, is that loud? I think it's better to you and me not having that echo on top of that. So, welcome to a new lecture of electrical stimulation. You should have received an email with a link to the Ilias page and a password. When I did that, I knew why I postponed that to that late point of time. That system is a nightmare, like Camtasia here in the background. So there are some things that are really not pleasant, but I think it should work out well. I do not expect that you read the complete book that I put there. But I thought it could be beneficial if you want to browse through, if you want to have a look. The book should be with the index, so you can check up certain keywords and then find out where things are. And sometimes it's beneficial if you don't understand what one person is saying, probably look in another paragraph where another person tries to explain the same things in different words. So that might probably guide you a little bit through and gives you the help if you want to have that. So also uploaded the old slides, and we'll check up what I change from slide to slide. Sometimes I discover very old typos or things like that there, and that comes on then there as soon as I have it, but there are no major changes. What is not yet there is the summary that comes at the end, and the last lecture about sensory feedback, because that lecture does not yet exist. So that will be then in next year uploaded there. So again, here the link in one line and the password, so it should be easy for you to access that. Nevertheless, I'm more than happy to have you here in a lecture, that you can ask questions, that we can get in contact, which I find much better than just online, offline downloads, whatever stuff there. Good. The old lectures might be 4 to 6 pages per page or whatever. I'll store the new ones one slide per page. If you like to use that for annotations or whatever, that you have more space over there. Good. We were diving into electrochemistry last week, which is not the most pleasant topic on Earth, and we will go even deeper today. So, trying to bridge the measurement and instrumentation there with some wording and with some equations that are underlying, but which I will not use for that lecture, and which I have to admit I do not use at all also in research. But we all should have heard about these equations, that we get an idea when they are popping up somewhere, or we get asked, that we know they are around. And to give you an outlook for the next weeks, we will continue then after that electrochemistry with the question, how do electrodes look like? What are they good for? That you get an idea why this electrochemistry is used and how to apply that. That's the plan then for the next weeks. That measurement stuff that we had last week, the potentiostat, and the next slides are about how to measure that. There's always the question, what does an electrode do? So which information does it transfer? And what does it do at equilibrium? And then the next question is, are we in equilibrium or are we outside equilibrium? So if I have an electrode, and I'd like to remind you, the water window, about 1.4 volts at the interface. That's the important thing. It's just the interface there where this water window is important. what is the equilibrium? And I think we can probably agree that everything above the water window is outside the equilibrium for sure, since we are already creating gases. And if we are close to the boundaries, we are already in the range where some things happen. And if you browse through the tables that you got, you see, if you look in detail, oops, I can oxidize proteins there, or other longer molecules. There is something going on with platinum on the surface or something like that. So this is probably also not really much inside equilibrium. That means equilibrium is more if we are 10 millivolts or 100 millivolts, so in the smaller ranges. And you get some graphs already from last week to remind you what that is today that we can go through. So when we measure, the question is always how many electrodes do we need? And I think it's easy to agree that we need more than one. If we just put one electrode somewhere without any ground, we cannot measure it all. We need at least two to close the electrical circuit. And you already learned that some persons take three with a potentiostat, and I now want to go with you through those different arrangements. What is that good for? And what information do I gain? And what kind of information do I lose? And this is always done here on the next slides, that we have a kind of graphical display on the left-hand side, how it looks like. And then we take our magnifying glasses and a kind of, let's say, electrochemical probe or microscope and travel with that through the picture on the left-hand side. Don't ask me how we measure that in detail. That is not the question of today, but it's rather the idea to get a grasp what is happening there. And if we take this example, we have here a working electrode. Might it be a sheet of platinum that is on ground, and we have the reference electrode, and we address that topic, what the reference electrode is in detail over the lecture of today, but just take it as an electrode that knows what it does at the moment. And we have it on the other side, and we could then say, okay, if we have something like that, we could add here whatever kind of voltage source. Might it be alternating voltage or direct voltage? And then we could measure the current flow. And then we would get the complete voltage or the current when we apply a voltage over that picture. When a current is flowing from left to right, we have, as we've seen last time, an equivalent circuit. So the electrolyte might be probably kind of resistance type thing. There's something happening in the left-hand side electrode interface, and there's something happening on the right-hand side and the reference electrode. And this is here the electrical potential that we measure. And if we go now, let's say from ground to the entry of that electrode, that would be part A. So we have a resistance of the cable that is close to zero. That means if we have a resistance close to zero and we pass a current through, the voltage drop is also close to zero. That is part A. Part B is the interface of the working electrode, where we learned last time. This is a capacitor and a resistor somehow in parallel. And if we linearize that, we can say, okay, we have a voltage drop over the interface. That is what you can find if you look on that slide from last week with the Helmholtz double layer and the potential that is then increasing over that capacitive part of the Helmholtz double layer. That is here part B. C is the electrolyte, and in first approximation, the electrolyte can be modeled as a resistor. So another voltage increase there due to the current flow. And then we have D. That's here, the reference electrode. Now I have to go into detail. This reference electrode is made out of a tube, and this tube has a glass frit, and the glass frit, or here it's called the plug, is a very porous piece of material through which certain specific type of ions can pass. In this case here, we have chloride ions from the sodium chloride, the salt water, to the potassium chloride that is usual inside such an electrode, and the common denominator is the chloride. So chloride ions can pass through that plug or glass frit there. That's part D. Then we have part E. That's here the electrolyte inside the electrode. We have part F. That is the electrode itself. And then we have part G. That's the cable here. And if we now would measure, we could measure between the end terminals of that setup. That means we would have something like that, and I'm pretty sure I made a mistake, because if I measure between ground and ground, I measure nothing. So I did something wrong here, but I'm too close to that to see what I did wrong. But this is here, what we measure here. Right, yeah, probably, yeah. So, but my take-home message here, just discovered that, you're right, is that we measure a voltage and we cannot separate where it occurs. Yeah, if we would have, now looking into the future, saying we would implant electrodes and we could pass a current through these electrodes and would measure the potential in between the electrodes, we would never be able in such a setup to differentiate what is at the electrode, what is in the electrolyte, what is the tissue in between. We can make our assumptions, but we are not able to measure that. So if you think about this, if you who have survived control theory, this is the question, are variables observable? So if I want to predict something or estimate, I need the relevant parameters to do that. And some of those are observable, that means I can measure them, and others are non-observable. That means you have to make a good educated guess to find out what happens there. And this is where it comes to that point where you say, well, we measure something here, but it's really a pity that we do not know what happens at our electrode that we want to investigate here on the left-hand side, that electrode. And for that reason, and if we now do that inside the body, we are not able to have such a complex structure here with glass and a wire and whatever. So there's one group on Earth who implants that into humans, but all the others are a bit afraid to implanting glass pipettes in human brains. For obvious reasons, if you know how brittle glass is, you don't want to have something like that into the brain, and if somebody falls down, we have a lot of splints inside the brain. That doesn't sound that favorable. Therefore, we take here 2 electrodes like that, and with that we have the same story, and I don't read it out loud. You can do that by your own. We have the lead, the one electrode, the electrolyte, the other electrode, and another lead, and then you get the voltage over those 2 electrodes. In the 3 electrode setup with that potentiostat that we have. We also have these staggered approach, let's say with a lead, an electrode, the counter electrode, the electrolyte, and another lead and stuff like that. But with that electronic circuitry that we have, we apply in that case a voltage to the electrode that is then defined, and we measure the current through the electrode. And by that, having the current really through our electrode under test, we know what is happening at our device under test, and we can more or less blank out the rest. If you ask a very fundamental electrochemist, they would tell you, no, that's not completely true. We forget a lot of things that we don't consider. And what we forget here is that we have an electrolyte. So we measure the current through our device under test, and we apply through the other electrode that voltage, but we have a voltage drop over the electrolyte. Given that the body is modeled as physiologic salt water, 0.9% sodium chloride, we have a well-conducting media, and the voltage drop over that is negligible. If you go into sulfuric acid, phosphoric acid at low concentrations, this is no longer negligible, but due to my understanding, this is a stupid approach if it goes to the human body. That's excellent for fundamental electrochemistry, but we are not fundamental electrochemists. We want to do something for electrical stimulation in humans and want to assess what transfer characteristics do the electrodes there have, and therefore we model them in salt water. And by that we can just forget about that voltage drop. If you have to consider that you might stumble over a capillary that is called Haber-Lugin capillary, which is then used to compensate that voltage drop over low conductivity electrolytes. But this is far beyond, yeah?
So this setup does not help us to calculate out basically the voltage drop over the electrolyte.
Right. Wait a second, we come to the next slide. If you want to have the voltage drop, here, this comes later with a voltage drop over the electrolyte. If you can wait a little bit on that, please. So, and here, with the potentiostat in there, we can directly measure the transfer over our electrode at work. So as I said, we apply a voltage here. The reference electrode, put that potential over the second input terminal of the operational amplifier to the electrolyte here. And by moving the potential there, current flow occurs that is measured over our recording circuitry, and then we can divide one by the other and we get the impedance with magnitude and phase shift with the sinus signal that shifts the phase. The output here is the counter electrode that helps us to bring the current in that has to flow through our device under test. But the potential is described here with a reference electrode. If you want to have now the question, how does my electrode behave at different DC potentials, you can superimpose that DC potential over your AC potential and the input terminal. But this is then again fundamental neuroscience. And then you see if you're closer to the water window, you have a preference to certain processes to occur.
Okay, so this helps to kick out one, like the counter electrode.
Right. Because you never know if you have two of them and you measure over the whole thing, what is the influence of the counter electrode and what is the influence of my measurement electrode. If you are, let's say, if you take a very engineering approach, you say, well, the electrodes look the same, they have the same size, so I divide everything by 2, yeah, and split it up to both electrodes, and neglect the influence of the electrolyte in between. But since positive and negative reactions are sometimes asymmetric in kinetics, this works under certain limitations. If you really have small signals, if you have larger ones, you can say, well, let's take a larger counter electrode. It's very large, the current density drops down, and then we can neglect nasty processes there, things like that. But this is the real setup that you can look with magnifying glasses on your electrode and know that everything that you don't consider there is on a good side and does not influence your parameters there. And you already made that question, what about the electrolyte? And I like to rephrase that question a little bit. What about the things that are in between the electrodes? That could be the electrolyte, but that could also be the question, can I somehow measure growing tissue in between, or if something changes in between? If you have scarring after implantation, you might probably know how much scarring do I have? And the question would be, can I then differentiate the scar from a corroding electrode? Yeah? And the answer is it's not that easy. But the idea is here that you take 2 electrodes where you push current through and you measure then the potential. And I like to show that on the next slide what the idea is. The idea is if you have a current source, you don't take care what the potential at those electrodes is. You just don't care. You push a constant current or a controlled current at sinusoidal shape through the electrolyte. And if you know the geometry, let's say we take a capillary of a given length and a given diameter, then we have a cylinder, and we can then, by having the current passing through and the voltage that occurs, we get a resistance, and by geometrical calculations we can then go down to the specific resistivity that we get. And if something changes in between, then we can measure that. In an ideal case, you could say we have equidistance, so the same distance between the current electrode, first voltage electrode, second voltage electrode, and second current electrode. And by that equidistance, there are some field equations derived from the 4 Maxwell's equations, which show you that you then can calculate back to that resistivity in between. The assumption that we have to take is that the voltage meter has an infinite input impedance, so that no current flow occurs, and if no current flow occurs, we have no changes due to that current flow at the electrodes. That is the idea. It sounds a bit weird. An application here of that 4 electrode measurement idea is, for example, to investigate cells or cell assemblies. So if we have microspheres of cells that have been exposed to drugs, we could measure them in such a capillary to see if the drugs influence the well-being of the cells, for example. And in more practical ways, such an idea of applying a current and having a capillary is cell counting. There are counters where you in cytotoxicity measurements where you expose cells to certain drugs, and the question is, do the cells die or do they survive? and if they die, they are quite often resolved. And what is left over are vivid cells, and then you push or pull them through a capillary. And if you have a cell in such a capillary, the current flow would drop. And this could be detected then in a current voltage diagram, and by having those drops, you can count the cells. That is the famous Coulter counter. Company is called Coulter. This is a counter, and the Coulter counter is one of the workhorses in cell culture laboratories, for example. At the end, the question always is, if you know about those measurement techniques, which one can I use in my certain environment? So it would be always ideal to have reference electrodes there, but as we will see shortly, they're not that biocompatible, and they are difficult to use. So materials that are stable and work as reference are either the so-called saturated hydrogen electrode or reversible hydrogen electrode, RHE. This is a piece of platinum where you bubble enough hydrogen around. This is something you can do on the table in a beaker, but I would not volunteer to get a platinum wire implanted or on my surface where hydrogen is always bubbled around. That's not doable. The other thing is silver chloride, which we will address later on more in detail. This is good in general, but molecular silver is toxic, so nothing you like to implant on the brain. That's good if you put that on the surface of the skin for a limited amount of time. Then the silver works a kind of antibacterial and it doesn't hurt. That's fine. In chemistry, you use saturated calomel electrodes. Calomel is mercury dichloride, and mercury is highly toxic, so nothing you want to use in contact with living beings. So we will stick later on to the silver chloride electrode, which works well on a lab bench, works well on surface electrodes, does not work in this version with a tube around and a plug on the top for any biological application. And then we end up with 2 or 4 metal contacts. Just as a reminder for those of you who are not working every day with polar Cartesian transfer of impedances, just as a reminder how you can come from a length of a pointer and its angle between real and imaginary part to the real part and the imaginary part, with the idea that we have that angle theta due to a shift, a phase shift in a sinusoidal wave that we apply, all given under the boundary condition that we expect the frequency staying the same. Yeah, we never talk about that, but if we apply 50 Hertz, we always expect that we get 50 Hertz. And this is the truth under which we are working. So it's just the attenuation of the amplitude and a shift in phase. And remember, in biological tissues, we have no inductive components, so we have only capacitive components. Means no positive phase shifts are to be expected. We have always angles between 0 and minus 90 degrees. So what can we do? And here's the same graph on the left-hand side as Bode plot and on the right-hand side as Nyquist plot, where we can get an idea what does the electrode do, how does it work as a transfer function between input and output. And what we see here in the Bode plot is that we have a kind of high-pass behavior, so high impedance at lower frequencies and then a kind of constant value, and the rest here on the very right-hand side is not a miracle. That is the measurement error of the instruments where we took those curves. Very important for every one of us is to look on the y-axis. Here's the impedance. In some environments, people plot the output voltage or something like that. So we always should check what is on the y-axis, that we get a good idea how we have to interpret those things. And we get here an phase angle at about -70 something, and it goes down to 0, and we forget about everything we see over 200 over the high frequencies here, because that is due to some cables and connectors and the measurement equipment. And what we are talking about, just as a reminder, is that standard equivalent circuit of an electrode, where we have a capacitive part, a resistive part, and then the excess resistance there. And if we transfer that into a Nyquist diagram as shown on the right-hand side, so minus imaginary part over the real part, then we get that semicircle. And if we go towards much higher frequencies and everything is fine with the measurement equipment, we should really get the complete semicircle. And by having then the maximum value here and the two sections with the x-axis, we can derive then the components. If you really dive deeply into that, you will find out if there's a flattening of the semicircle, that does mean something, and depending on the right-hand side entry part, we can estimate certain properties of the electrodes at low frequencies. We lose the frequency information if we don't plot it next to the data points. And I always recommend, if you do those graphs, first of all, put some markers in where your measurement points have been. So something like that, or yeah. Because that helps you to see obvious interferences and artifacts. If you have then bumps at 50 Hertz, 100 Hertz, 150 Hertz, or if you are in the US at 60, 120, 180, this is an indication that you have interference with the line voltage, for example. In these cases, we don't see them because we know our tricks, how to play that. You have to say how many measurement points per decade you want to have, and you can say, oh, I'll take let's say 25, 50, 75, 100, then you have 4, and you hit perfectly well the multitudes of your line frequency. Or you say we take 5, then we have 20, 40, 60, 80, 100, then the 50 is not in and the 100 is already attenuated. So it's worth playing around with a number per decade or something like that. I always strongly recommend to have those whatever diamonds, stars, circles for the measurement points there. Also helps if you overlay certain things and you have problems with your colors, that you can still depict which curve belongs to what sign that you have in there. If we go towards stimulation, all those equivalent circuits have been mainly developed for recording, so small signals. If we go towards stimulation, we have to learn that we can create water. We can split up water into hydrogen gas and into oxygen gas. That means it always goes in one direction. And if you try to remember, if you have a voltage that goes to a certain limit and then it produces, let's say, immediate current generation, and you cannot go beyond that limit of voltage, that element is called a Zener diode. And this is shown here. These are the Zener diodes. That means you can go in reverse direction up to that potential, and then it opens immediately and brings you, well, kind of infinite current. This is what happens if you generate oxygen. Yeah, then you have permanent charge generation due to putting two O minuses together to O2, and the charge goes over your system. And the same in the opposite direction is hydrogen. So if you look on the second row, then you see we have that generation voltage as a diode. We have a resistor that gives you the voltage drop, and then we have the Zener diode there for that current generation. That is the extended model, having also a voltage drop on the Faradic resistance. This is stolen from an English textbook, therefore the electrolyte resistance is Ra from excess resistance, and we have the phase boundary where we have the Helmholtz capacitive and then the sometimes this the other resistance there. You get your measurement data, and then you want to see what model do I have, what parameters can I extract, and this helps you if you take some software, depending which program you have or what you write by yourself. You can start with certain elements, and if you take this simple equivalent circuit instead of the complex one, and you look on the measured data and the fitted result, you're quite close. And this is always then the question of the application side: how close should you be? You can model things very complex in very strange things. The question always is, what do I need? And if it comes to electronics design, and you would like to match the load of your stimulator with the load of the electrodes and the electrolyte, you have to be realistic. The stimulator knows only inductances, resistors, and capacitors. Electrochemistry knows many more elements, and then you have to find a trade-off and a balance where you say, well, I know that I should do it better, but I can only use what I have on the electronic side, so it's probably more clever to model your outside world, the electrodes, with that, what you have on the electronic side, to get the conjugated complex value there for load matching. That's always, that's something that electrochemists hate, but it doesn't help, because if you have to develop a recording circuitry or a stimulation circuitry, it should match best the reality, and that means you have to work with what is available on the electronic side. Yeah. Yeah, that's fine. I say it. I thought I'll wait for a question or not. We have the generalized impedance is defined as whatever value over j omega to the power of n. If n is 0, you have a resistance, right? So that goes, and I'll do it down here, n equal to 0 is R. N equal to 1 yeah, that's the capacitive thing. In this case, is n equal to -1, then we have the inductor with j omega L. So far, so good. In electrochemistry, n goes from -1 to +1 element of R. That means we have something where we have an n equal to 0.7, for example. That's called a constant phase element, which gives you an indication how rough your surface is, for example. It goes far beyond this course. That's the reason why I did not put it on the slides. You cannot, it's hard to model that. In those expensive softwares, you have those elements. It helps you in failure mode analysis, for example. If you have an electrode and you measure that electrode, and after 3 years of stimulation, you measure it again, and you see that the model has a different exponent, then you can find this as an indication of corrosion because the surface roughness got larger, for example. Or there's if n is equal to 0.5, this is called an Warburg element. So the German guy Warburg, 1899, discovered that. I stole that, I copied that paper once, was of course highly forbidden to copy a paper from 1899. And I was not able to read it. So there were equations, I knew the values, but I could not link the equations with the language that was there. It was so old style. And that guy found out that you have a resistance. If n is equal to 0.5, you get something where you have a real part and an imaginary part, and the real part is dependent on the frequency. That means a resistor that depends on the frequency. That's really weird because the resistor should be independent of frequency. And this is something you can imagine, that there are diffusion processes at the surface, and at a particular roughness, this hinders the charge to go over the surface. And this is then really Champions League electrochemistry, let's say, when it comes here, for example, in clean room developments, where we try to tailor nano surface structures and have to find out if this is beneficial in charge transfer, or if the aspect ratio, so the depth to surface ratio, is such that charge carriers are generated but cannot reach the target tissue. It's also called overpotentials. And this is something that goes beyond the let's say, the intuitive understanding of those interfaces, but is well described in electrochemistry. But those elements are such that you cannot match them with electronic circuits. And this is the point where you have to find the trade-off. You know then that your description is wrong, but it's the best possible wrong description to match it with a recording equipment, for example, or a stimulation equipment. Those of you who don't want to dive that deeply into that now wake up again. We are back to definitions. And one important definition is the charge delivery capacity. That gives us an idea. What is the maximum amount of charge that I could drive reversibly or irreversibly over an electrode under equilibrium conditions? And equilibrium means in this case that we are slow. And being slow means we raise the potential slowly over a straight line to return potential and go back. And this is something we do for several times. And we do it once, we get a kind of hysteresis curve if we plot the current over the voltage. So this is here the voltage, and you get that in detail on one of the next slides. And we use a 3-electrode setup with a potentiostat there. We have slow potential rates, we measure the current, and the area under the curve is called the charge delivery capacity. Sometimes people take care and say, we go back and forth, so probably the charge delivery is only half of that, because if we go anodically, it's delivered and if we go back cathodically, it's redrawn or withdrawn there. And therefore, some people say it's only half of that. And slow means slew rate, so voltage per second change is probably 10 millivolt per second, 100 millivolt per second, really slow stuff. This is nothing that resembles a rectangular stimulation pulse. And you can imagine if you should go through a forest and you go slowly, you can go around all trees, let's say. If you should run, you have to make your way, and probably less persons can run through a forest than can go slowly. And if you compare that, and a person would be a charge carrier, so probably more charge carriers can pass somewhere if it goes slowly, as here, as it goes when it goes fast with a stimulation pulse. And therefore, and I try to get a little bit more light in here, at least with the lamella there. If you go faster with a rectangular current pulse, this is then called charge injection rate. So injection is something that goes fast. And here, information about the charge delivery is what happens at the interface. Forget about the charge injection. I thought it comes first and goes then back. So we go back here to the charge delivery. So this is good to find out which reactions occur at the surface of the electrodes. So is there platinum dissolution or not? Is there iridium oxide working well, or doesn't it work at all? For us, one very important finding is always, are the electrodes open? So if you make microsystems, you quite often have sandwich structures. So you put in an insulator, you put in your electrode with a cable, you put a top layer insulator, and you open the top layer insulator to come to the electrode. When the top layer insulator is still closed, you have no electrode. Yeah? It sounds stupid, but that's one of the most often failure cases, that something changes and the electrode is closed. And if you know I have platinum there and you do such a cyclic voltammogram, you can differentiate, do I see the platinum reactions or not? If I see them, everything is fine. If I don't see them, I made a mistake. Yeah, this is something what you can do. And this is how it looks like. And now it's too much sun again. We have the voltage course, which is triangular, upper left-hand side, and we measure the current. And if we then plot the current over the voltage, and this is here for one complete cycle, and this is a real curve with 100 millivolts per second slew rate on a platinized platinum electrode. That means we have put rough platinum on the surface to see even more reactions on a given geometrical area. We see those oxidation and reduction peaks here, these bumps, that bump, the other bump there, and this bump there. And if the voltage is increased, they occur at a certain potential, and if we reverse that, we see that the reversed reactions occur at different spots, or other reactions occur there. We know where the water window is when the current goes up steeply. Yeah, and then when I see, oh, this is now the water window, we go probably a little bit back, that we do not come into that irreversible reaction. If you know, might be a bit suspicious that we have minus 0.9 and plus 0.6 something volts there, it's because this has been done versus SCE. That's saturated calomel electrode. That's this electrode containing mercury. This is different from silver chloride, where the whole the whole graph is a little bit shifted by, I guess, 0.05 volts or zero point 0.1 volts. But the rest is the same. And here's what happens if we take that. We have the anodic part up there with reversible hydrogen evolution. We have H atom plating, so that PTH that we have seen. We have PTO, so oxidation and oxygen evolution. If we reverse that, we have the reversal of O2 evolution, the reduction, H atom plating. That means where the H atoms are going away, they're coming back here, and then we have hydrogen evolution. If we would have a very smooth curve, so if you get something like that, you still get the hydrogen and oxygen evolution, but you do not see any bumps in there. This is a purely capacitive electrode, could be gold, for example, or it's where your insulation layer is still on your electrode. In the case of iridium oxide, you remember that fancy material that does not like to decide if it's 3 times positive or 4 times positive, depending on the potential. We get this very characteristic bump shape, and here we overdid that a little bit. And by overdoing that, you get continuous processes that increase then the amount of charge transfer. That is good on one hand side, and that is called an anodically formed iridium oxide film. That works in salt water. You do that, and the salt water reacts with the iridium. It's not the salt, it's the water, the OH and the H that reacts with the iridium, and the smooth metal gets into that iridium oxide structure, and more iridium oxide is growing. If you now imagine iridium versus iridium oxide, there's the oxygen part that has to be placed somewhere in the lattice structure of the iridium. And that means it gets more spongy. Well, it's not a sponge, but it gets larger. And in the worst case, it flakes off. And if you imagine you have a bulk material, it grows something on top, and that part flakes off, then you have lost already part of your bulk material. And if you redo that several times, it's like corrosion at the end. You have no bulk material left. And that was one of the reasons why that anodically formed iridium oxide was at one point of time no longer that fashion anymore, because of those hazards. That was the point where persons were able to deliver out of the clean room sputtered iridium oxide films. That's a really cool thing. You put you take a sputter machine and an iridium target, and you bump out those iridium particles that fly over the vacuum to your substrate where they should get deposited, and on the way to that, they meet some oxygen atoms. That's called reactive sputtering. And in air, there's already a reaction of iridium with iridium oxide, and so if they get deposited, they have already that iridium oxide structure and are put on top of the base layer. There are some tricks how to perform that process, but all in all, that works well and stays really stable without that changing properties and without the hazard of flaking off. If you coat something, you can increase the surface roughness and the surface reactivity, depending what material that is. In the case of platinum, it's just the roughness. Shown here in very old and not that nice SEM picture, instead of a smooth layer, you have a kind of grainy structure there due to the deposition of platinum. And if we look on the curve, you can hardly see the red curve. That's the charge transfer, charge delivery capacity of platinum. And if we put that on top, we see a much larger curve to get that platinum. It's so micro rough that it appears black in the microscope, since it does in a light microscope, since it does no longer reflect the light, and therefore it's called platinum black. Platinum black has a disadvantage because it's deposited out of a solution that contains a lot of lead. Lead is toxic. Therefore, it has been banned from any medical applications. That means for the use in humans. There have been some tricks that persons try to deposit it from a non-platinum based solution where it's not that rough, and this is then called either platinum gray or platinum brown. And one of the two is patent pending. I cannot remember which one. But it's not the surface roughness, it's just mainly due to the fact that people don't want to have lead in their processes. Now, if we stimulate, we normally don't want to know all those details. What we want to know is how much current can I push through the electrodes without driving them into corrosion. And the idea is, if you can drive the electrode up to the water window, then it's still fine. So, being a bit naive and looking on the last slides, we've seen the water window is a little bit around 1.4 volts. If I would now send you out for shopping, you would find that most of the commercially available stimulators go at least up to 10 volts. And the question is, why? If I destroy electrodes at 1.4 volts, why am I able to buy stimulators that are nearly tenfold of that? And here comes any good ideas from your side? Just stupid or educated guesses, I take everything. No? No famous coatings. So no Merlin showing up and doing some miracles. So no famous coatings. If you look on that curve here, this is how the potential looks like after a current pulse. Any idea where the water window interface could be here? No idea? I help you out with that. So, if we take our stupid, simple equivalent circuit model, and we have a current pulse over time, it looks like that. And we push it through that circuitry. What we get is an immediate step response at that first excess resistance. And after that, pushing still current through, we charge the capacitor. That means this here is the potential drop at the excess resistance. Potential is I times R. And for that reason, this is in some textbooks called the IR drop. took me some years to find that out. That IR drop means it's the potential that is generated by the current flow over the excess resistance. And this part here goes over the other part. Yeah, capacitor, resistor. And this is the phase boundary where the water window is. That means if we are brave, we could say we subtract the IR drop and look that we drive then the remaining parts to the limits. Unfortunately, and this is not clearly shown here, is that the anodic and the cathodic part are asymmetric. There are different kinetics in the anodic and cathodic reaction, so it's not really true that we can take those electronic the electrical equivalent circuit elements. There's something more behind that, but that means we drive only that capacitive part up to the water window and can add the voltage drop over the excess resistance. And if you imagine, we might have muscle tissue, blood, vessels, fatty tissue in between our electrode and the counter electrode. This is the part that needs all of these volts in stimulators as voltage swing to drive the current that we eventually need. Yeah, the question was, can we model it as MOSFET? I wouldn't say so. You're right with the threshold, but all the MOSFET, a lot of MOSFET modeling is done with GM over ID, so with the transconductance, and that would mean we would assume, or we would get a picture that we can change something on the transconductance, and therefore I would not feel very comfortable to model that in that way. I don't say that it's not possible, but I would not feel very comfortable because the association that you get with that is different to what we expect here. You were fine with your question? Good. Because I think it's important to get that to the point and ask questions. There are no stupid questions around, you know, and there are other things that you can read on the slides. And if you can read it on the slides, I don't have to explain it in detail. This is here something where I got, always you do something, you put it on, and this is a good example what you should not do, this slide. The black line is a reversible pulse. As you see here, this is voltage over time after a current pulse. So we applied the current pulse. And if you have that capacitive charging curve that you know from textbooks, then you're fine. If you overdo that, you get the red curve where you have funny changes in curve shape. And this is when you create whatever corrosion. Yeah, that means here you get an overpotential, and that could mean that you dissolve platinum particles from the surface that go somewhere. And if you reverse that, you get another shape. And if you do that more often, you lose your electrode. That was the hard part for today. Now we are going a bit into what is around and are there some classification schemes. First of all, to the reference electrodes, that you get the slides to find them. So this is the reversible or standard hydrogen electrode, which is the 0 point of all electrochemical reactions. And then you get a reactivity list depending at what potential does what happen. And as I already said, with that bubbling hydrogen, this is good for chemistry, this is not good for medical engineering. We find here the electrochemical series, the half-cell potential, so-called. That means we have the noble and the noble metals, the noble metals with a high electrochemical half-cell potential, and the others with a low half-cell potential. The only thing that might be surprising for you is aluminum. Well, we all know we can take aluminum for the alloys on the wheels. We can take it for whatever heavy stuff that means that survives in harsh environments. And now I tell you it's not a noble metal. So how does that work? The solution for that is that aluminium forms a very stable aluminum oxide surface layer as a native oxide, which is very stable. And that means we do not see aluminum outside, we always see aluminum oxide. And then it stays stable. And in contrast to iron, you could now say, well, but if I put iron out in the rain, I get rust. And if I wait long enough, it goes away. That's true. The trick is that the aluminum oxide is very stable and has a relatively low intrinsic stress compared to iron oxide. And therefore it stays in place and forms a closed layer, while iron oxide has a relatively large stress. That means we have pores that break open, and then it gets flushed away, and new iron is exposed to the environment and transforms in iron oxide and goes away, and that means our iron rusts away. Good. So we can classify according to many different aspects. Could be metallic, non-metallic, and I skipped that here completely. There are materials like graphitic carbon, like graphene, conjugated polymers. That is nothing which is covered here. It's highly exciting, but I think we should not overdo it here. And then we have non-reversible electrodes that are used as chemical sensors. That's also not topic of this course here, therefore they drop out. Sometimes you find polarizable and reversible, irreversible together. I also made that mistake for several years and found out this is probably something that we should separate. So we have irreversible and reversible electrodes. That is second type, first type. And we find the reference electrodes here. That looks like our favorable pathway. But in practice, we use quite often metal electrodes. And that means we know they're not the best, but if we take certain boundary conditions into account, we can work with them. Yeah, like many things we do that we know this is not the best possible thing, but we have no good alternative for that. Yeah? Yeah.
Because we learned this polarizable and reversible stuff for the last time.
Yeah, that's right for recording, that doesn't fit for stimulation. So if it's polarizable, you have it polarizable, yeah, but in this case, you're right.
In the last slides, I always found it confusing which belongs now to what.
Yeah. So it's you can put it together under equilibrium conditions for recording electrodes, but then when I went to stimulation electrodes, I decided once, so we should not put that together for stimulation because we are not in equilibrium. And my suggestion is probably to have this here to bring a bit light into the dark, so that we rearrange things that makes it clearer where it goes. So we have redox reactions, or we have redox reactions where we have an electron transfer, and we're focusing on the electrode transfer. This is mainly in analytical chemistry. Yeah, where we focus on how many electrons are transferred over a platinum electrode, and by that we can get an idea which metabolite is analyzed or something like that. And I don't say that you cannot do it differently, but probably that helps a little bit for our purpose. And then we are looking more on the ions. And probably we can, I don't know if we really need that here, that electrons or ions, because if we have electrons, there's also, yeah, an electron never comes without a counter ion. So you always have it on both sides. Yeah, so I'm not sure if this line helps or not. When I made it, I thought it helps a lot, but looking now from different perspectives, it can be probably also a bit confusing. And then we have polarizable and non-polarizable ones. And metals are polarizable. If we stimulate, we don't care that much about polarization because we push the current through. And if there's a voltage period. Yeah. If we record, we don't want to have an additional potential on our small signals. At the very end, it comes back together when we say we want to record and stimulate over the same electrode. Then we need a material that fits both requirements. And this is here the key thing with the equilibrium. If we stay inside a certain equilibrium, metal is fine. If we go outside, we come to trouble. With the reversible electrodes, and those of you, I know some of you had already biomedical instrumentation 1, we have here that silver chloride electrode with the reactions at the phase boundary. That silver goes into silver plus, and then chloride minus comes, and then it forms silver chloride, and that silver chloride can split up again. The chloride goes into the solution, the silver goes back to the wire, and we have that reversible S reaction here. And this stays constant in the potential as long as we have enough chloride ions in the solution. So if a little bit of change in the chloride does not change the logarithm, then we are fine. And that means having large numbers, and large minus 5 is still large. If we have a high concentration, then the potential stays stable. As said, molecular silver is cytotoxic, so this is good for surface things, for analytics, but not for implants. If we do really redox reactions where we calculate the charge that goes somewhere, then we are in analytical chemistry. This is here more important. Where are we on the electrochemical potential series? If we have silver chloride, we are at 222 millivolts. If we take calomel, here mercury dichloride mercury, then we are at 267, so 45 millivolts apart from silver chloride. More important for us is the silver chloride, and that means if you look up in an electrochemical potential series that something is at 1 volt, and we have silver versus hydrogen, reversible hydrogen electrode, and we have silver chloride at 222, then you have to go from 1 volt to about 800 millivolt. Yeah, or the other way around, depending if it's positive or negative. Since I always gets crazy with that subtraction and addition, and not only me, but all the others, the convention is that we don't take that calculation into account, but tell the reader with which reference electrode we are working. And then it says on the x-axis voltage versus silver chloride, and that helps us all. That's all I wanted to say. Here we have just a copy of those things that some of you already know, electrical circuit modeling. If we have polarizable electrodes, we might end up here with a polarization potential in series to that equivalent circuit thing. And the polarization, again, is the additional potential that occurs if a current is flowing. Current voltage diagrams means if we have a polarizable electrode, we get a lot of potential if we have a certain current density here. The small j means current density, so current over area. If we have a non-polarizable one, we get much more current through without getting an additional overpotential eta. We can live with transfer overpotentials and diffusion overpotentials due to the material itself or to its surface roughness. We can tailor that a little bit, but we can live with that. We cannot live with reaction and crystallization overpotentials where we change the material as such or destroy it. That's counterproductive with respect to longevity. If you dive deep into electrochemistry and electrodes, you will cross the Volmer-Butler equation, which looks not very friendly since we have the exchange current. The sum of all redox currents S all is a sum of two components that describe how current and potential belong together. The potential here is it here? That's here the reorganization energy. You see the temperature goes in. We have the proportionality factors, and then here the energy. If we solve that with respect to the exchange current density, we found out that this depends here on a symmetry factor and the potential. So that means current flow and applied potential are non-linearly linked in that. So forget about Ohm's law. Yeah, depending on the potential that we apply, and if it's positive or negative, we have a different exchange current density that goes over the phase boundary. This is to be considered if we're talking about biophysics, if we talk about molecular analysis, so you can see how much dopamine you have or other neurotransmitters when you learn something about electron transfer at interfaces with carbon electrodes or something like that. This is normally not considered in electrical stimulation since we are so much out of the equilibrium that we do not consider that. But it's important to know that there is something in the background where you can describe all the details at the interface. At the end, I like to browse with you through, let's say, very standard electrode materials. And I like to stay a bit apart from what can be done with a clean room and thin film technology, since most of the clinical applications are still precision mechanics. So we buy that somewhere and don't manufacture that in a clean room. And it's always a trade-off between performance and cost. And if your performance is good and stable with something that is less pricey, you take the cheap one. Only if there are good reasons, you go to more expensive stage. And the easiest thing that you get is stainless steel. It's more or less non-corrosive. And if you polish that you have a defined surface, you can use that well. On the other hand, if you look a little bit deeper in material science and you have to process stainless steel somehow, then temperature might come into the game, and then you see, for example, carbon accumulation in stainless steel at the grain boundaries. In other grain boundaries, you see carbon depletion in grain boundaries, and this could be then a starting point of grain boundary corrosion. Therefore, people say, well, we are not that happy with stainless steel. Let's take alloys where we have cobalt, chromium, manganium in to have a better distribution of grain boundaries, of grain size over the material, and the more homogeneous that is, the less grain boundary corrosion we can get, and to counterfeit grain boundary depletion. And that is MP35N, that's the brand name, and another brand name that is very famous or has been very famous was Algiloy. That is a bit different in the alloy composition, but is all with cobalt, chromium, and manganium. Now you can pop up and say, hey, we learned that cobalt and chromium might be toxic or allergenic. That's completely true. Therefore, these materials are no longer that much in the forefront in developments. But still, they are, at least as cables, as supporting structures, they are very stable. And if you know that they do not corrode under cathodic pulses, there's still some applications where you are monophasic, you can use them. They can also be coated with carbon to increase the surface roughness. And this is kind of golf ball effect that was very, very under research 20 years, 30 years ago, where people said, well, those golf balls with their surface structure, they don't have less turbulences. Can we use that for medical engineering because it looks so cool? And then they did it and found out, well, we don't have turbulences in electrical stimulation, but if we consider the edges that we have there, we have higher current densities there and a better charge transfer at these edges. And there have been cardiac pacemaker electrodes that look like golf balls. And I think part of that was really sales argument that could have been designed differently. The standard material still is platinum iridium, and this table is strongly linked to cardiac pacemaker electrodes with the statements there. Platinum iridium is very good, highly non-corrosive, long-term stable, but it still corrodes. Yeah, there's nothing that does not corrode. And the statements have been made in textbooks at a time where people did not look that carefully into that. Since 2 years, there are the first long-term studies on corrosion of cochlear implants. So explants have been carefully investigated, and you can easily see that platinum iridium corrodes over 25 years under permanent stimulation. So that means some redesign rules will be a bit more focused on that. You can make platinum iridium porous to enlarge the surface and reduce the polarization voltage and impedance by having more surface in a small area. And then you can define what is porous, what is microporous. Probably nowadays it would be nanoporous because it sells better if nano is somewhere in the word. So it depends. The idea is always the same, having a larger electrochemical active surface area over a defined geometric area. Titanium nitride is also very fashioned. Some of you might know it from tool making. So tools for whatever, grinding, milling, drilling, get much harder if they get a titanium nitride coating. But it can be also used as stimulation electrode. It's a capacitive electrode. It has a high double layer capacitance. But we have to take care that it does not break when we overdo anodic stimulation. That means we have to carefully check how it works and how stable it is. And in micro machining, it's used in a way that you generate structures that look a bit like Giant's Causeway. So we have a kind of hexagonal pillars standing next to each other, and by that it increases the surface dramatically. Yeah, because you do not only have the surface, but you have the side walls of those pillars that contribute to the charge delivery. And if you imagine that as additional area for the Helmholtz capacitance layer, you get a lot of more. However, if you overdo that and have a wrong aspect ratio, so too high pillars with not enough space in between, this charge that comes over the Helmholtz double layer is not able to contribute to the certain distance because it gets stuck into the interpillar structures, and then you get a downside. That means it's a kind of optimum where you get best possible charge delivery, and after that it drops down again. And this is something that you have to find out for your process, for your application there. PVD means here physical vapor deposition, so mainly deposition in vacuum here. We can have iridium. If you see here, we have platinum iridium here, and then I switch to iridium, and some of you might think, so isn't that the same? No, it isn't. The platinum iridium, and forgot to say that, it's mainly 90-10, so 90% platinum, 10% iridium, or 80-20. And that means the iridium is not the key contributor, but it's added there into an alloy to get better mechanical strength. If you bend platinum, you easily break it after 10 times bending. If you have platinum iridium alloy 90-10, you can bend it probably for 10 to the power of 5 or something like that times, and it's still stable. So it's just the mechanical part for the electrode. Iridium is good, but as said, you know, we have that iridium oxide thing, so we have to see how it works. It was mainly used in the early days to enlarge the electrochemical surface, and by doing that, people found out, oh, we can oxidize that, oh, isn't that cool? And then it went from iridium to iridium oxide, and process technology is done. So as already said, since you asked that earlier, that electrode classification might be misleading when it comes to stimulation electrodes, since we are really working far outside the equilibrium. So with that, I'm at the end for today, and hope that you got a little bit an idea why electrochemistry might be of importance. You don't have to like that, you just have to admit that it might be of importance. Here's the summary. So we like to minimize the energy when transferring charge over the electrodes. We should have a low tendency to irreversible formation of electrochemical and inflammable reaction products. That's one of the reasons why carbon is now so much on the top side, because carbon is known to be pyrogenic, thank you. Losing a bit words. That means it does not contribute to inflammation. We want to have low polarization at the phase boundary, long-term stable transfer characteristics, and we do not want to see artifacts there due to whatever, movement, electronics, things like that. And this has to come then on the long-term run with the price, with the costs that we have. And just as an example, if you have in manufacturing, and this is an old example, so it's even worse nowadays, the price that I have in mind was 3 to 5 years ago. So 10 centimeters by 10 centimeters stainless steel sheet, 20 microns thick. It's probably around 50 to 100 euros, while platinum iridium of the same size, 10 centimeters by 10 centimeters, 20 microns thick, is about 1,500 euros. Having now the price increase into mind, probably we're now even higher. I recently got the information about our clean room, for example, an iridium target. So that size, 2-3 millimeters thick of iridium, is now somewhere around 120,000 euros. That means even if you don't need much for making thin film electrodes, if you would imagine you would have to run a company and you have to add all the costs, it needs a rock solid fundament to have that money around if you need some additional material. And it's the same for silicone rubbers, for stainless steel parts. So the costs are relatively high, and therefore the goal of all engineering approaches is to use small amounts of money and to get out with high yield, that you don't have to throw away too many things there. This is beyond those, let's say, more theoretical requirements that we have. For you, the last slide to get a little bit the idea, what should I know for the oral exam? You should know the different measurement methods and be able to explain them and a little bit assess what is good for what. Should be able to say something about electrode classification. Probably also some contradictions that have popped up. It's not that I want to have the ultimate truth, but that you are able to discuss based on your knowledge pros and cons of those things, and that you're able to explain the electrochemical mechanisms and discuss a little bit what electrode would you use for what purpose or not. With that, I'm at the very end. Thank you very much. Next time is about how do electrodes now really look like, and where do I put them? What can I do with them? That's the task of next week. More practical, less theoretical. And with that, I thank you very much for staying here and wish you a nice week and hope to see you again next time. Thank you. Bye-bye.